G'day guys, in this video we'll be going over derivatives by first principles. So what are they, how do they work, and why are they useful? And maybe the best place to start this conversation is, what is a derivative? And the answer to that is that it's a rate of change. And a rate of change is for every given increase in x, what is the increase in y? And I'll just demonstrate that for you with a linear line. Okay, so here is the Cartesian plane, and what I want to offer you is this linear line. Alright, so now let's say we pick 2 points on this line, here and here. Right, remember that definition of the rate of change. It's that for every given change in x, what is the change in y? So here we have 2 points, so there will be 2 x coordinates and 2 y coordinates. And we can call this x1, y1, and we can call this x2, y2. Nice. So here we have a increase in x, and the increase in x is this much, and we can call this delta x. That triangle is a delta, and it is just shorthand for change. So when we have this change in x, we have this corresponding change in y. Okay, so that's really cool, but I want to show you another linear line. Alright, let's say we have the same starting point, and let's say we keep that initial change in x. This time, this is our change in y. Right? So if we look at that red line, same change in x as the orange line, but for that change in x, the change in y is much greater. So we can say that has a steeper gradient. Okay, so that's really cool. And we actually have a formula for gradient. And we can say that the gradient, sometimes people call it m, that gradient equals y2 minus y1 over x2 minus x1. And the other way we can write that, y2 minus y1, that's just the change in y. We can actually write it as delta y over delta x. And that's the reason why it's division, right? Because it's the ratio. For every change in x, how much is there a change in y? So it's a ratio, and that's why it's division, and that's something really cool to point out. Okay, so this works really well with linear lines because the gradient or the rate of change is consistent, so it's constant. You'll always have a constant rate of change because it's linear. And so that means that any 2 points you pick on the line, if you plug them into this gradient equation, you'll get the same value. So that's really cool. Okay, so here's a slightly different example. What about a line like that, a parabola? How can we calculate the gradient at any given point on the parabola? Right? And maybe the first question is, well, why is it different? And it's different because any point you have on the parabola, that instantaneous gradient will always be different. Okay, and so the question is, how do we calculate the instantaneous gradient? And it's a very good question, and this is where first principles comes in. This is why first principles is useful, because it allows you to calculate the instantaneous gradient on a line that is not linear. So how do we do it? Okay, we can call this x and we can call this y. And we can say that this is a function of x, and this looks like 2x squared. If I pick 2 points on this graph, and I calculated the gradient as if it were a linear line, I would actually get the average rate of change between the 2 points. And I can call this x value x. And I can call this x value x plus h, right? And this distance here, that's h. What happens if h gets smaller? We might have a point here, because we're not having as much distance. Further still, what if h gets even smaller? This distance here is h. We get closer and closer to the instantaneous gradient at point x. This is something really interesting to point out. We can have two points, x and x plus h, and as h gets smaller and smaller, we actually approach the instantaneous gradient at point x. So that's really cool. So how does that math work out? First step is to pick the 2 points. And we can choose x. Now, when x equals x, what does y equal, right? And by kind of definition of that function, f of x, we know y equals 2x squared. That's cool. So that's the first point. Right, so what's the second point? We can just say x plus h. And when we substitute x plus h in terms of x, what does that y value equal? The y value is 2 times x plus h squared. And if that doesn't make that much sense to you, that's okay. What we're doing is we're taking this x plus h value, treating it as its own value. We could call it a, we could call it b, we could call it z. I'm just calling it x plus h. And if we substitute that value, x plus h, into f of x, what is the y value that we get? And the y value that we get in terms of x and in terms of h is 2 multiplied by x plus h squared. Yeah, cool. So those are the 2 points. Okay, so if we remember that gradient m equals y2 minus y1 over x2 minus x1. We have a y2 and we have an x2 and we have an x1 and we have a y1. So let's do some substitution. We have 2x plus h squared, y2 minus y1 minus 2x squared over x2, x plus h minus x. Alright, so that's cool. And we can simplify this a little bit further. So we have on the bottom, on the denominator, we have x, a positive x and a negative x. So they can cancel out. So 2 multiplied by x plus h squared is x squared plus 2xh plus h squared. And then we have minus 2x squared just on the end over h. We can multiply everything out on the top. 2x squared plus 4xh plus h squared minus 2x squared. And this is handy because we have a positive 2x and a negative 2x, so they cancel out. We just have h on the bottom. So we're left with h squared plus 4xh divided by h. And we can factor out the h on the top because it's a common factor. Now this is really cool. The h's can just cancel out. And what we're left is the gradient m equals h plus 4x. Now, remember what we were saying. As h approaches 0, we get closer and closer to that instantaneous gradient at point x. So, this is something really key to think about. As h approaches 0, we can just substitute 0 for h. And I can show you a fancy way of writing that. We can take the limit. The limit of h plus 4x as h approaches 0 equals, again, we can just substitute h equals 0, 0 plus 4x, right? And that's just 4x. What this means is that the rate of change at point x of that function f of x is 4x. That's really cool. And we can just extend this a little bit further. What's the gradient at point x equals 3? This is really cool because we can just substitute x equals 3. We can just substitute x equals 3 into that gradient function. For x, 4 times 3. Nice. So this gradient function, this rate of change function, is known as the first derivative. And that's the entire definition of the derivative at the start, right? It's the rate of change of a function. That's all the derivative describes. And I can give you some fancy notation to impress your teachers too. If f of x equals 2x squared, then f prime of x equals 4x, right? F prime of x, this thing, that's the same notation for the derivative function, for the gradient function, for the rate of change function. We can also say dy over dx equals 4x. D for delta, for change. Y is like f of x. It's the change in f of x over the change in x. And so those are the two most conventional ways of notation. All right, that's all I got. Cheers. Subscribe if you liked it.